Hi guys, welcome back. We're going to now look at some problems where we're solving for the final velocity given initial velocity, acceleration, and time. So when we look up here at our notes, we're saying what is the final velocity? If you have an initial velocity, you know the rate at which it's accelerating and you know the time it takes for it to accelerate. Okay? So we have sample problem D, and then we'll go right into another sample problem. And from there, you should be able to complete practice D below. All right, so again, we'll use that same old guess method that we've been working with. So we start with our givens. A plane starting at rest, so that's a VI is 0. Again, that starting at tells me it's an initial velocity. One end of the railway undergoes uniform acceleration of 4.8 meters per second. So my A is 4.8 meters per second squared. For 15 seconds, my time is 15 seconds. What speed will it take off? So my final velocity is my question mark, or my unknown is what is the final velocity. So we're listed over there. All right, so we need an equation. And the equation provided for us is the final velocity of an object is its initial velocity plus any acceleration, and that depends on the time that it accelerates. So now we're going to solve the equation, and the equation, since my unknown is VF and I'm looking for VF, I'm good to go right there. I just have those two responses, so there's no manipulation of the equation. So VF equals VI, 0, plus acceleration times the time it took it to accelerate. And so we're now going to solve that expression, and that would be VF equals 4.8 times 15. And the final velocity of this object, we just simply multiply that out. Keep hitting that. And we get 72. All right, let me check that. Something seems funny. We get 72 meters per second. And so if we think about what's happening, it's getting faster by about 4.8 every second for 15 seconds. So what this solution says is every second we get, leaving out a word, faster by, I'm going to round that to 5 meters per second. So 15 seconds, about 5 every time. So 10 seconds would be 50. Another 5 would be 25. 50 and 25 is 75. So 72 is really close. So that's a little thought process we can do there, where we take 4.8 and we round it to 5, because it's about 5. And we know that acceleration means that's how much you're getting faster every second. So for 15 seconds, 5 every time should be about 75. So our answer of 72 is correct. Now, what else can we do with acceleration, displacement, time, and initial velocity? Well, we can also determine the displacement of an object. So up here we're saying, hey, find the velocity. Down here we're saying, hey, find the displacement. So we have a new expression that we haven't used yet, and it is the displacement is the initial velocity times the change in time plus 1/2 acceleration t squared. So we'll use this sample problem D as a practice problem. So we list our givens, and it says to use info from the sample problem D. So we know VI is 0 meters per second. And we know A is 4.8 meters per second squared. And we know time is 15 seconds. Now we also now know VF is 72 meters per second. But I want you to take into consideration that we calculated the 72. So I don't want to use that unless there's no other way, because I might be taking an error from one calculation and placing it into another. So what is our unknown? Determine how long the runway must be. So we're looking for how long the runway must be. And so that is the change in distance is our unknown. So we need an equation, and the equation is the displacement of an object is dependent on the initial velocity and the time it took for it to travel, plus 1/2 the acceleration and t squared. So we just solve that expression, and since we're looking for delta x, and our equation is already written in terms of equal to delta x, we don't need to do any special substitutions or anything there. We can just go right into solving this expression out, okay? And so we're just going to, let's bring this back down here. We're going to say the displacement of this object is equal to the initial velocity, 0 times the time, just 15 seconds. Of course, that multiplies out to be 0, plus 1/2 the acceleration, 4.8 meters per second squared, times the time squared. Most common mistake here is that we forget to square the 15. So be sure you don't forget to square that 15 when you're solving this. So our final response would be the change in x is 0 plus, go ahead and multiply this 1/2 times 4.8 to give us 2.4 meters per second times 15 squared will be times 15 again. And so our change in x equals, so just get our calculator here, and we'll go 2.4 times 15 times 15. Obviously you can use the square function if you'd like to. We get 540, and that would be a meter. And we check our significant figures. The question had 2 significant figures. Our response has 2 significant figures. So we're good to go on that one as well. So these are examples of sample problem D. 1, where we have the same givens, but we're solving for different things, okay? So we have the same givens, but in case 1, we're solving for the final velocity. Same givens, but solving for displacement. And there's 2 equations for that. There we go. Here's our next one.